Red Sea, which is now under constant threat by Iranian-backed Houthi rebels.
The U.S. is there to destroy missiles launched by Iranian-backed militants.
We've seen a reduction in their activity.
In the past 15 months, the U.S. Navy has fired more air defense missiles in the Red Sea than in the entire 30 years since Operation Desert Storm. This relentless barrage, like a storm battering the seas, has pushed American naval forces to their tactical and logistical limits as they face an enemy deploying advanced drone technology at a fraction of the cost. But the Navy's most effective countermeasure isn't missiles. As Houthi forces escalate attacks on commercial shipping, military strategists have turned to a weapon that doesn't fire a single shot. The electronic battlefield is now the front line, with remarkable results to follow. The Red Sea crisis, a choke point under siege. The Bab el-Mandeb Strait is one of the world's most critical maritime choke points, handling 12% of global trade annually. Over $1 trillion in goods pass through this 18-mile wide waterway each year, connecting the Mediterranean to the Indian Ocean. Its strategic importance became evident in October 2023, when Houthi attacks began disrupting commercial shipping. Major carriers like Maersk and Hapag-Lloyd were forced to reroute vessels around Africa's Cape of Good Hope, adding 10 to 14 days to transit times and increasing fuel costs by 30%. This diversion impacts roughly 15% of global container traffic that typically transits the Red Sea. The economic fallout has been severe. Insurance premiums for Red Sea voyages have surged by 400%, with some underwriters refusing coverage altogether. Shipping companies now face an estimated $1 million in additional costs per diverted voyage. Consumer goods prices have risen by 2 to 4%, due to extended supply chains, while energy markets experience volatility as tankers take longer routes to avoid the danger zone. European natural gas markets in particular have been hit hard, with prices fluctuating based on Red Sea security conditions. The ripple effects extend to manufacturing, where delayed component deliveries have slowed production. The Houthis initially targeted ships with Israeli links, but their attacks now threaten nearly all maritime traffic. Unlike Somali pirates who sought ransom payments, these attackers aim to create political leverage in their regional conflict. Crews operating in what was once a secure shipping lane now face constant threats. The psychological toll on merchant mariners has been significant, with many refusing to sail through the area. This conflict marks the first sustained attack on international shipping by a non-state actor with state-backed military capabilities. The Houthis have demonstrated the ability to disrupt one of the world's busiest trade routes using relatively inexpensive weapon systems. Their attacks have caused shipping volumes through the Suez Canal to drop by as much as 40%, creating bottlenecks in global commerce. Delayed deliveries, increased manufacturing costs, and volatile energy prices are just some of the consequences. The Houthis' strategy is to maximize economic disruption with minimal resources. They use drones and missiles to target commercial vessels, often justifying their actions politically. Their access to commercial satellite data and maritime tracking systems suggests external support, while their ability to sustain coordinated attacks over months highlights significant logistical backing. The cumulative effect of these disruptions represents one of the most significant shocks to global trade since the COVID-19 pandemic. Houthi drone tactics, the swarm strategy. The Houthis have developed a drone warfare strategy that prioritizes quantity and coordination over sophistication, systematically exploiting vulnerabilities in modern defensive systems. Their attacks often begin with waves of small unmanned aerial vehicles, UAVs, carrying minimal payloads. These drones act as decoys, triggering radar systems and forcing expensive missile intercepts. Once defenses are engaged, follow-up waves deploy more capable drones armed with explosives or equipped as spotters for missile strikes. This phased approach depletes defensive resources and exposes gaps for the main attack. Central to this strategy are two drone models. The Kasef-1 operates with a 500-mile range and a 30-kilogram warhead, while the more advanced Samad-3 boasts a 932-mile range and improved guidance systems. These drones, incorporating Iranian-designed components like inertial navigation systems, can strike deep into international shipping lanes without relying on constant GPS updates. Modified for maritime operations, they use infrared sensors to identify targets, making them particularly effective in disrupting naval operations. The cost disparity between attacker and defender underscores the asymmetry of this conflict. A single Houthi drone costs roughly $2,000 to produce, while U.S. Navy interceptors range from $150,000 to $3.5 million per missile. This creates a staggering cost ratio of 75 to 1 to 1,750 to 1, making sustained defense economically unsustainable. Even with perfect interception rates, the financial burden heavily favors the attacker. For example, a single missed intercept could result in significant damage to a commercial vessel, while the Houthis can afford to lose dozens of drones without comparable losses. Adding to the challenge, the Houthis launch these drones from mobile platforms hidden across Yemen's rugged terrain. These include modified trucks, fishing vessels, and even camel-mounted racks in remote areas. This decentralized network ensures that destroying one launch site merely shifts operations elsewhere. Launch teams require minimal training, allowing for rapid replacement and continuous attack capability despite coalition counterstrikes. A December 2023 engagement highlights the effectiveness of this approach. The USS Mason, an Arleigh Burke-class destroyer, faced 14 simultaneous threats over 90 minutes, including drones and anti-ship missiles. The ship expended 7 SM-2 missiles before switching to electronic warfare and its 5-inch deck gun. The attack followed a familiar pattern. Initial drones forced missile expenditures, subsequent waves tested remaining defenses, and final missiles targeted the ship when its systems were most stressed. This relentless pressure exposes the limitations of current naval defenses. The Navy's missile inventory, designed for Cold War-era threats, struggles to adapt. Ships carry limited missiles with reloads requiring days in port. At current expenditure rates, a single week of heavy combat could deplete a vessel's armament. While electronic warfare and close-in weapon systems offer partial solutions, they cannot fully address the economic and operational strain. This evolving threat has forced a re-evaluation of naval defense strategies as the psychological and logistical toll of sustained swarm attacks continues to grow. Electronic warfare, the silent killer. The AN/SLQ-32 electronic warfare system, known as Slick 32 among naval crews, has become the U.S. Navy's most cost-effective countermeasure against Houthi drone threats. Instead of relying on expensive missiles to destroy incoming drones, it disrupts their guidance systems, causing them to crash harmlessly. Each engagement costs only a few dollars compared to the hundreds of thousands required for kinetic interceptors. This efficiency allows the system to operate continuously without depleting finite missile inventories, a critical advantage in prolonged conflicts. Think of the Slick 32 as a digital shield, intercepting invisible arrows before they can strike. Unlike missile intercepts that produce visible explosions, electronic attacks leave no physical evidence. Drones simply lose navigation capability and plummet into the sea, leaving adversaries unable to assess which attack succeeded or how they were countered. In March 2024, the USS Gravely demonstrated this capability by disabling 6 incoming drones electronically, saving an estimated $9 million in missiles. Such engagements rarely make headlines, but are among the most tactically significant victories in the Red Sea campaign. The system's effectiveness lies in its ability to adapt to complex challenges. It identifies, classifies, and jams multiple threat frequencies across a broad spectrum, while avoiding interference with friendly systems. Modern versions use advanced signal processing to distinguish between hostile drone control links and civilian radio traffic. Machine learning algorithms further enhance its capabilities, recognizing and adapting to new threat patterns in real time. This adaptability is crucial against adversaries who frequently modify their drone systems. Jamming protocols vary depending on the threat. Against GPS-guided drones, the system transmits false positioning data, causing the UAV to miscalculate its location. For radio-controlled models, it overwhelms the command link with noise or inserts malicious commands. Some protocols target specific components like altimeters, tricking drones into descending into the water. The system can even create false radar returns, confusing drone targeting systems into misidentifying ship locations. The psychological impact of these operations is profound. Houthi operators never receive confirmation of successful strikes when their drones vanish without explanation. This uncertainty degrades their ability to refine tactics, forcing them to adapt blindly. Navy electronic warfare officers report noticeable changes in enemy behavior after successful jamming, with subsequent drone waves often using different frequencies or flight patterns in futile attempts to counter the system. Recent engagements highlight the system's evolving capabilities. In one instance, a Navy destroyer redirected a drone swarm back to its launch site. Another operation exploited vulnerabilities in Iranian-supplied control systems, shutting down an entire wave of drones. While the system has limitations, Its effectiveness decreases with range and struggles against drones using optical or inertial guidance. It remains a cornerstone of naval defense, a silent force multiplier shaping the future of electronic warfare. Growler dominance, the electronic combat game changer. The EA-18G Growler has become the U.S. Navy's most versatile asset in the Red Sea conflict, combining advanced electronic warfare capabilities with precision strike options. Each aircraft carries two ALQ-99 tactical jamming pods capable of disrupting enemy communications and radar across entire threat sectors. These pods generate focused beams of electromagnetic energy that can simultaneously target multiple frequency bands used by Houthi drone control systems and early warning networks. The system's directional antennas allow precise targeting of enemy assets while minimizing interference with friendly systems. In July 2024, a Growler assigned to Carrier Air Wing 7 made history by achieving the first confirmed air-to-air kill against a Houthi drone using an AIM-120 AMRAAM missile. The engagement highlighted the aircraft's dual role in electronic and kinetic warfare. Initially, the Growler jammed the drone's control links, but when the target continued its approach, the crew transitioned to a missile strike. This adaptability underscores the Growler's ability to counter evolving threats in real time. The Growler's ANAPG-79 Active Electronically Scanned Array AAESEA radar enhances its effectiveness by detecting and classifying signals 300% faster than legacy systems. Its simultaneous air-to-air and air-to-ground modes allow continuous tracking of airborne threats and surface-based launch sites. During a March 2024 mission, a single Growler detected and jammed 6 separate drone control stations while guiding strike aircraft to their targets. One crew member later described the mission as a constant balancing act, requiring split-second decisions to prioritize threats while maintaining coordination with allied forces. Electronic attack missions have yielded substantial results since operations began. Growler sorties have destroyed 23 Houthi radar sites and 17 command centers through a combination of direct strikes and electronic targeting support. The aircraft's ability to geolocate hidden facilities has enabled follow-up strikes by other platforms, amplifying its strategic impact. For example, during a February 2024 engagement, 2 Growlers working with an E-2D Hawkeye disrupted an entire wave of 14 drones through coordinated jamming and deception techniques. The ALQ-99 pods operate across 5 distinct frequency bands, covering all known Houthi communication systems. Each pod generates up to 10 kilowatts of effective radiated power, with reactive jamming modes that counter new signals automatically. This automation allows a single Growler to manage multiple electronic battle spaces simultaneously, a critical capability against adversaries who frequently adapt their tactics. The Growler's combat record in the Red Sea validates its role as a cornerstone of naval strategy. Its unmatched combination of electronic warfare, precision strikes, and carrier-based mobility ensures rapid response to emerging threats, securing dominance in contested environments. Naval guns, the unexpected comeback. The U.S. Navy has rediscovered the tactical value of its 5-inch deck guns in countering drone threats, offering a cost-effective alternative to missile systems. Each 5-inch round costs approximately $500 compared to $150,000 for a Hellfire missile or $2.1 million for an SM-2 interceptor. This staggering cost difference makes naval gunnery the most economical option for close-range engagements. The Mk-45 Mod 4 gun system, mounted on Arleigh Burke-class destroyers, can fire 20 rounds per minute with an effective range of 13 nautical miles against surface targets. When drones breach the outer defense perimeter, the immediacy of gunfire becomes critical. Sailors often have less than 8 seconds to acquire, track, and engage a target. The USS Carney showcased this capability in November 2023, destroying 3 Houthi drones in rapid succession using only its 5-inch gun. This engagement not only saved an estimated $1.5 million in missile costs, but also demonstrated the precision and reliability of naval gunnery under pressure. Unlike missile systems, which operate on a fire-and-forget principle, gunnery requires constant human involvement, creating a unique psychological dynamic. Crews face intense stress as each missed shot provides immediate visual feedback, heightening the urgency of their task. New ammunition types have further enhanced the gun's effectiveness. Proximity-fused shells equipped with radio frequency sensors detonate near a target, significantly increasing the probability of a kill. These rounds compensate for tracking inaccuracies and evasive maneuvers, improving hit rates by 40% compared to standard high-explosive shells. This innovation has proven critical in countering small, maneuverable UAVs. The resurgence of naval guns has also prompted changes in training and tactics. Sailors now undergo advanced courses in drone engagement and rapid target acquisition. Simulations include realistic drone profiles, and live-fire exercises emphasize quick engagements against multiple small targets. This shift reflects the Navy's focus on adapting to modern threats while maximizing the cost-effectiveness of its arsenal. Operationally, the guns complement missile systems in a layered defense strategy. Ships conserve missiles for long-range threats, reserving gunfire for drones that penetrate the inner defense zone. The USS Mason demonstrated this approach in February 2024, using missiles against an initial wave of drones before switching to guns for subsequent attacks. This 47-minute engagement resulted in 8 drone kills, with minimal missile expenditure after the first phase. While continuous use of the guns accelerates barrel wear and increases maintenance demands, their mechanical reliability remains high. Crews now perform daily inspections to ensure readiness, and the Navy has bolstered ammunition stockpiles to sustain high-tempo operations. Compared to missiles, 5-inch rounds are easier to store and replenish, ensuring ships remain combat-ready during prolonged engagements. This logistical advantage, combined with the gun's proven effectiveness, underscores their vital role in modern naval warfare. The Aegis system under pressure. The Aegis combat system, originally designed during the Cold War to counter large, fast-moving missile salvos, now faces a stark mismatch against modern threats in the Red Sea. Its SPY-1 radar can track over 100 targets simultaneously, but fire control limitations restrict engagements to just 12 threats at a time. This becomes critical when facing coordinated drone swarms that overwhelm the system's capacity. These drones, like the Samad-3, have radar cross-sections nearly 100 times smaller than conventional anti-ship missiles, making them harder to detect. Imagine a vigilant guardian scanning a crowded horizon but struggling to spot a flock of sparrows darting through the chaos. The reduced radar signature compresses warning times from minutes to mere seconds, leaving little room for error. The USS Mason's February 2024 engagement highlighted these vulnerabilities. Over 6 hours, the destroyer faced 18 waves of drones and missiles, firing 32 interceptors before exhausting its missile inventory. Forced to rely on electronic warfare and its 5-inch gun, the crew managed to fend off the final waves, but the encounter underscored systemic challenges. While the Aegis system successfully tracked all threats, it couldn't engage them all simultaneously, exposing a critical gap in its architecture. Software updates have improved threat prioritization, helping operators focus on drones with direct attack profiles rather than decoys. However, human operators still make final engagement decisions, creating bottlenecks during high-tempo attacks. Even with intensive training to compress decision timelines, physiological limits remain, especially during prolonged engagements. The Red Sea's unique environment compounds these issues. Coastal terrain, commercial air traffic, and temperature inversions create radar clutter, masking small drone signatures. Adversaries exploit these conditions, routing drones through radar shadow zones to further reduce detection times. The cost imbalance in countering these threats is unsustainable. Each SM-2 missile costs millions of dollars, while drones like the Samad-3 are built for a fraction of that. This dynamic forces the Navy into a costly game of attrition. Adding to the strain, each missile launch requires support from the ship's SPG-62 radar, which can only guide 3 interceptors at once. This hard limit forces difficult triage decisions when multiple threats converge. Maintenance demands have surged under the operational tempo. The SPY-1 radar requires frequent calibration and cooling system checks, with crews now performing daily diagnostics instead of weekly. The Red Sea's harsh environment accelerates wear on sensitive components, further reducing system availability. To adapt, the Navy has accelerated development of the SPY-6 radar, which promises better performance against small targets. Training has also evolved, with simulation scenarios now emphasizing drone swarm tactics. Operators are trained to recognize swarm patterns and optimize weapon allocation, but these adaptations can only mitigate, not eliminate, the system's fundamental limitations. Guns versus drones, the cost-effective alternative. The U.S. Navy's 5-inch deck guns have become a vital defense against drone swarms, offering a cost-effective alternative to missile interceptors. Each 5-inch round costs about $800, a stark contrast to the $500,000 price tag of a Standard Missile-2 or the $4.3 million for an SM-6. This cost disparity highlights the unsustainable nature of relying solely on missiles for close-range threats. The Mk-45 Mod 4 gun system, mounted on Arleigh Burke-class destroyers, achieves a 70% hit probability against subsonic drones with proximity-fused ammunition, transforming naval gunnery into a frontline defense tool in the Red Sea conflict. The USS Carney showcased this capability in March 2024, destroying 6 Houthi drones in 22 minutes using only its 5-inch gun. The engagement began when radar detected multiple low-altitude UAVs. With missile systems depleted from earlier attacks, the crew relied on gunfire as the drones breached the inner defense zone. Each successful intercept saved approximately $1 million compared to missile alternatives, underscoring the financial and tactical advantages of naval gunnery in modern warfare. Proximity-fused ammunition has revolutionized the effectiveness of these guns. These rounds detonate when their sensors detect a nearby drone, increasing the likelihood of a kill without requiring direct hits. Testing shows a 40% improvement in success rates compared to conventional high-explosive rounds. To meet the growing demand, the Navy has tripled the ammunition load for these guns on deployed ships, reflecting their critical role in fleet defense. Drone engagements place immense pressure on gunnery crews. When a UAV breaches the outer defense zone, sailors have less than 10 seconds to acquire, track, and fire. The USS Mason demonstrated this in February 2024. Destroying 3 drones in quick succession during a nighttime engagement. Using thermal imaging to track targets through sea spray and smoke, the crew operated with precision under extreme time constraints. This level of coordination between radar operators, fire control technicians, and gun crews is essential for success. Unlike automated missile systems, naval gunnery demands constant human involvement. Crews experience heightened stress as they see the immediate results of each shot. Missed rounds splash visibly in the water, while successful hits explode against the skyline. This hands-on nature creates a unique psychological dynamic compared to the detached process of missile intercepts. The Navy has adapted training and tactics to reflect the gun's new role. Advanced courses now focus on drone engagement and rapid targeting, while live-fire exercises simulate realistic UAV scenarios. Ships can serve missiles for long-range threats, using guns for closer engagements as seen in the USS Laboon's April 2024 operation, which neutralized 7 drones in 35 minutes. The unsustainable math of missile defense. The U.S. Navy's missile expenditures in the Red Sea have reached unsustainable levels. Since October 2023, the service has fired over $9.2 billion worth of interceptors against Houthi drones and missiles, an amount that could fund an entire new Arleigh Burke-class destroyer with its complete weapon suite. The cost imbalance is staggering. Each Houthi attack package costs approximately $500,000 to assemble, while defending against these threats requires $15 million in interceptor missiles. This 30-to-1 cost ratio heavily favors the attacker, even with perfect interception rates. In one engagement, the USS Laboon fired $28 million in missiles to neutralize just $800,000 worth of threats. Such exchanges are economically unsustainable and threaten broader naval readiness. Stockpile levels have already dropped to concerning thresholds. By January 2025, SM-2 inventories fell to 45% of recommended wartime levels. The Navy typically maintains a 30-day supply of missiles for major contingencies, but current usage rates far outpace production capacity. Raytheon, the primary manufacturer, has increased production to 40 missiles per month, but each SM-2 requires approximately 18 months from order to delivery due to complex manufacturing processes. This lag creates critical vulnerabilities if conflicts escalate elsewhere while resources remain committed to the Red Sea. Missile maintenance requirements compound the financial strain. Each SM-2 interceptor requires 20 hours of maintenance for every hour of flight time, and the Red Sea's harsh environment accelerates corrosion and component wear. Technicians now work 18-hour shifts to keep systems operational, with some ships reporting 300% increases in maintenance hours compared to peacetime operations. Forward-deployed technical teams have been added to address the crisis, but human factors limit how much the maintenance tempo can increase. Operational patterns further exacerbate the problem. Ships often fire multiple interceptors against each threat to ensure destruction, rapidly depleting inventories. For example, during a March 2024 engagement, the USS Mason launched 3 SM-2s against a single drone to guarantee interception. While the Navy has adjusted rules of engagement to permit single-shot engagements in some scenarios, the fundamental economics remain unfavorable. Supply chain limitations restrict rapid replenishment. Missile components come from hundreds of suppliers worldwide, with some critical parts requiring lead times exceeding 12 months. Storage facilities in Bahrain and Djibouti now operate at maximum capacity, but this logistical network was designed for occasional combat operations, not continuous high-intensity engagements. These challenges, combined with the financial strain, leave the Navy facing difficult trade-offs in other theaters, risking vulnerabilities and potential conflicts with near-peer adversaries. Iran's technological hand. Iran's technological support has significantly advanced Houthi drone capabilities, transforming them into a formidable threat. Weekly shipments from Iranian ports to Houthi-controlled areas in Yemen include guidance systems, turbine engines, and advanced avionics for precise maritime strikes. Iranian Revolutionary Guard Corps (IRGC) technicians have been documented modifying drone designs in Houthi workshops, creating a clandestine assembly line of innovation. Tehran's strategy relies on intermediaries and shell companies to obscure its involvement, a model it has perfected across its proxy networks. The technological transfer focuses on critical systems absent in commercial drones. Recovered Houthi drones feature Swiss-made MS-2100 inertial navigation units, identical to those in Iranian Shahed 136 drones used in Ukraine. These 18,000 systems enable GPS-independent guidance, crucial when satellite signals are jammed. Chinese-made TJ-100 turbojet engines power long-range models, extending their reach beyond 1,000 kilometers. Components arrive disassembled through Oman and Somalia, with final assembly in hidden Yemeni workshops. This covert supply chain sustains production rates of 15 to 20 drones monthly while evading international sanctions. Western commercial technology is also embedded in Houthi drones. Investigators found Texas Instruments microprocessors in guidance systems and Swiss U-Blox GPS modules in communication systems. These dual-use components, intended for civilian applications, are repurposed with Iranian-developed software to enhance maritime targeting. One captured drone even contained a modified Samsung tablet running waypoint navigation software. This blend of commercial and military technology complicates interdiction efforts while reducing costs. Iranian intelligence networks provide targeting data to the Houthis. IRGC operatives use commercial satellite imagery from providers like Maxar Technologies to track ship movements in the Bab el-Mandeb Strait. Signals intelligence from Iranian reconnaissance aircraft and ships supplements this data. Encrypted satellite phones and mesh radio networks relay the information to Houthi launch crews, enabling precise attacks in the strait's narrow channels. This system mirrors Iranian proxy operations in Iraq and Lebanon, but with a sharper maritime focus. Houthi production facilities have grown increasingly sophisticated. Underground workshops near Sana'a now produce composite airframes that reduce radar signatures. Thermal imaging reveals 24/7 operations powered by Iranian-supplied solar arrays. Standardized assembly lines and improved quality control have reduced failure rates from 40% to under 15%, reflecting an industrialized approach uncommon for insurgent groups. Training programs further bolster Houthi capabilities. IRGC instructors conduct monthly courses on drone assembly, maintenance, and targeting. Graduates train others, expanding the knowledge base. Practical exercises use captured merchant ships as targets, producing 50 to 70 qualified operators each quarter. Meanwhile, the U.S. Defense Innovation Unit, DIU, races to counter these advancements. By leveraging commercial technology for affordable, rapidly deployable solutions, the DIU aims to disrupt the clandestine assembly line fueling Houthi operations. This contrast highlights the ongoing battle between adversary innovation and U.S. response initiatives. The DIU's race for affordable solutions. The Defense Innovation Unit has launched an urgent initiative to field counter-drone systems within 12 months, compressing the traditional multi-year acquisition cycle. This accelerated timeline directly addresses the Navy's unsustainable expenditure rates in the Red Sea. DIU requirements specify systems must achieve engagement costs below $10,000 per kill, while countering simultaneous drone swarms exceeding 50 targets. These parameters demand a complete rethinking of cost structures and technologies. Traditional defense contractors face steep challenges meeting DIU's aggressive targets. Established missile systems, costing $100,000 to $3 million per engagement, far exceed the required threshold. Even stripped-down interceptor variants struggle to break the $50,000 per shot barrier. Beyond munitions, costs for tracking systems, command infrastructure, and maintenance compound the problem. DIU evaluators have rejected multiple proposals for failing to address total lifecycle costs, forcing companies to pursue more innovative solutions. One unconventional proposal adapts anti-tank missiles for drone interception. A defense startup suggested mounting modified Javelin missiles on unmanned surface vessels, leveraging existing designs while eliminating expensive naval-specific components. Each 30-pound interceptor costs approximately $8,000 within DIU's target range. The unmanned platforms provide mobile launch points, positioning themselves between commercial traffic and threat axes. Testing shows the modified missiles can engage drones at ranges up to 2.5 miles, with 70% success rates in controlled environments. Microwave-directed energy weapons offer another promising approach. Compact, high-power microwave emitters can disable multiple drones simultaneously. One prototype mounted on a literal combat ship achieved 80% effectiveness against drone swarms in recent tests. The system pulses focused microwave energy to fry electronic components within a 30-degree cone. Each engagement costs roughly $500 in electricity, making it potentially the most economical solution. However, range constraints under 1 mile and atmospheric attenuation during poor weather remain challenges. Hypervelocity projectile technology bridges the gap between energy weapons and kinetics. Originally developed for railgun programs, these tungsten projectiles travel at Mach 5 when fired from standard 5-inch naval guns. Guided by miniature radar seekers, they can intercept drones at ranges up to 5 miles. Each round costs approximately $3,000. Far cheaper than missiles while maintaining precision. The Navy has accelerated testing, with initial operational capability possible within 18 months. Ships can carry hundreds of these projectiles compared to dozens of traditional interceptors. Electronic warfare solutions are evolving rapidly. New systems actively hijack drone control links, redirecting threats. One DIU-funded project demonstrated the ability to take over Houthi drones mid-flight, landing them intact for analysis. This approach neutralizes threats while providing valuable intelligence. Tests have achieved 60% takeover rates against current Houthi drone models. The DIU's fast-track evaluation process compresses traditional testing protocols into 90 days. Selection criteria emphasize modular designs that integrate with existing ship systems. Winning proposals receive immediate funding for at sea testing in the Red Sea, where operational feedback drives rapid iteration. Combat tempo. Warships push to the limit. Destroyer crews in the Red Sea now endure grueling 18-hour combat shifts during high-threat transits. Sailors rotate through 4-hour sleep periods while remaining at general quarters for the rest of the time. The USS Mason's crew, for instance, spent 47 consecutive days at this heightened alert status during peak operations. Fatigue has become a critical factor, with medical officers reporting a 300% increase in stress-related cases compared to standard deployments. Crews must stay constantly vigilant against drone swarms that can appear with little warning, pushing both personnel and equipment beyond their limits. The USS Laboon's March 2024 engagement highlights the intensity of these operations. In a single 90-minute battle, the destroyer fired 42 missiles, 85% of its standard loadout. After exhausting its missile stores, the crew relied on electronic warfare and the 5-inch gun to counter follow-on threats. This level of weapons usage has forced the Navy to establish forward reloading stations in Djibouti and Bahrain, but even these measures often leave ships returning from patrols with depleted magazines. Weapon systems are also under immense strain. The Aegis SPY-1 radar, which typically requires 20 hours of maintenance per week, now demands 60 hours due to continuous use. Missile guidance systems must be recalibrated after each firing, a task once reserved for port but now performed at sea. Gun barrels, designed to last 5,000 rounds, now require replacement after just 1,500. These accelerated wear patterns are reducing overall system readiness, despite increased maintenance efforts. The human toll is equally severe. Sailors describe the psychological strain of watching drone feeds for hours, never knowing when a real attack will come. One USS Carney crew member recalled, "You're always on edge, waiting for the next alarm." Over 12 weeks, the Carney conducted 37 intercepts, with sailors enduring more than 100 general quarters alarms. This relentless pace affects decision-making and operational effectiveness, compounding the challenges crews face. Material costs and logistical challenges further strain the fleet. The Navy spends $1.5 million daily on missile interceptors during peak operations, while fuel consumption has surged 40% due to defensive maneuvers. Supply chains are stretched thin, with missile inventories at regional depots dropping to 30-day levels. Critical spare parts face 6-month back orders, forcing rationing and prioritization for combat zones. The operational tempo is reshaping the Navy. Training cycles have been compressed and medical support expanded to address both physical and psychological impacts. Yet, the long-term consequences on ships, sailors, and fleet readiness remain uncertain. The future of naval warfare. The Red Sea conflict has showcased the first large-scale use of drone warfare in a maritime setting, offering critical insights into the future of naval strategy. A Naval War College survey found that 78% of serving officers believe unmanned systems will dominate strike missions within 15 years. This shift highlights the cost asymmetry in current operations, where $20,000 drones provoke million-dollar interceptors. These lessons are reshaping naval combat, influencing ship design, legal frameworks, and international partnerships. One immediate challenge is the legal ambiguity surrounding drone operators. Houthi technicians launch attacks from civilian areas, complicating targeting decisions and raising questions about whether operating a drone constitutes direct participation in hostilities. Current international law lags behind these realities, leaving gaps that adversaries exploit. The U.S. Navy has developed internal protocols, but these remain untested in international courts. As drone warfare expands, updated legal frameworks will be essential to address these dilemmas. The Navy's next-generation DDG-X destroyer reflects this evolving landscape. Its design prioritizes counter-drone capabilities, allocating 40% more deck space for directed energy weapons and specialized bays for interceptors. Traditional anti-ship missile defenses have been scaled back in favor of systems optimized for smaller, more numerous threats. These changes signal a shift in naval priorities, moving from peer-state conflicts to asymmetric challenges like those seen in the Red Sea. Adversaries are also adapting. Iran, for example, has supplied advanced drone technology to its proxies, enabling precision strikes that disrupt shipping lanes and challenge U.S. dominance. This shadow war underscores the urgency of counter-drone innovation. The Navy's Project Overmatch has deployed AI-controlled gun systems capable of identifying and engaging drones autonomously, processing data 50 times faster than human operators. Early tests show 80% effectiveness against swarms, though the ethical implications of autonomous weapons remain contentious. Electronic warfare is evolving to counter these threats. Predictive algorithms now anticipate drone swarm behavior, enabling systems to redirect entire waves by spoofing navigation signals. In one demonstration, an experimental system successfully neutralized a swarm by targeting its lead unit. These capabilities could transform electronic warfare from a defensive tool into an offensive weapon, with operational deployment expected by 2026. The shift in naval strategy mirrors historical transitions, such as the move from sail to steam. Training now emphasizes drone threat recognition and swarm engagement tactics, while the Naval Academy has introduced coursework on autonomous systems. Supply chains are also adapting, with forward-deployed ships carrying larger quantities of low-cost interceptors to sustain high-volume engagements. International partnerships are forming to address these challenges. The U.S. and 12 allied navies are developing standardized protocols for counter-drone operations, marking a shift from traditional alliances to collaborative asymmetric defense. These efforts reflect a broader reimagining of sea power, where distributed lethality and smaller, more numerous platforms define the future of naval warfare. Iran's Shadow War Technology Transfer Network. Satellite imagery reveals a steady flow of arms shipments from Iranian ports to Houthi-controlled areas of Yemen. Commercial satellites capture Iranian vessels unloading cargo at Al Hudaydah approximately every 9 days. These shipments include disassembled drone components, missile guidance systems, and communications equipment. The vessels follow circuitous routes through international waters before transferring cargo to smaller dhows near the Yemeni coast. U.S. intelligence estimates 70% of Houthi drone components originate from these shipments, with the remainder sourced through smuggling networks. This operation ensures a consistent supply of advanced weapons while maintaining plausible deniability. Houthi technicians receive advanced training at Iranian Revolutionary Guard facilities near Tehran and Qom. IRGC records show over 200 Yemeni personnel completed 6-month courses in drone operations and missile maintenance since 2021. The curriculum includes hands-on instruction with Shahed-136 drones, identical to those used against Ukrainian infrastructure. Graduates return to Yemen to establish training cells that replicate Iranian programs, enabling the Houthis to maintain and upgrade their systems independently. This knowledge transfer ensures technical expertise remains available despite coalition strikes on senior leaders, reflecting Iran's broader strategy of empowering proxies to sustain operations under pressure. The drone guidance systems incorporate components from sanctioned Chinese manufacturers. Recovered Houthi drones contain Chengdu J-10 turbojet engines and Nanjing-based radar altimeters. These components enter Iran through front companies in Malaysia and the UAE before transshipment to Yemen. Chinese firms supply 65% of the electronic components in Houthi drones, including navigation computers and communication modules. While U.S. sanctions disrupt some supply chains, alternative procurement routes emerge within weeks, with components often disguised as agricultural equipment or medical supplies. This adaptability highlights how evolving supply networks sustain long-term operations. Iranian technical advisors maintain a continuous presence in Yemen, despite official denials. Imagery from Sana'a workshops shows Iranian engineers supervising drone assembly lines. These advisors, operating undercover as humanitarian staff or commercial representatives, provide real-time troubleshooting and quality control. Rotating every 3 months, they ensure technical standards match Iranian capabilities while avoiding overt military links. This mirrors Iran's broader doctrine of embedding expertise within proxy forces to enhance operational effectiveness. Production facilities in Yemen now replicate Iranian manufacturing techniques. Underground workshops produce composite airframes that reduce radar signatures, while assembly lines follow standardized processes to ensure consistent quality. Redundant production sites mitigate coalition strikes, enabling the Houthis to produce 15 to 20 drones monthly. This manufacturing capability, combined with centralized repair depots and modular designs, demonstrates how non-state actors adopt state-level practices, reshaping the future of asymmetric warfare. The Red Sea conflict has shown that 2,000 drones can challenge a $700 billion navy, underscoring the need for innovation. Systems like the AN/SLQ-32, with an 80% success rate against drone swarms, highlight the shift to non-kinetic warfare. Cost-effective tools such as 5-inch guns and hypervelocity projectiles prove legacy systems still matter. Forward-looking initiatives like Helios lasers and new DDGX specs aim to cut engagement costs from millions to thousands, addressing asymmetric threats. Yet with insurance costs 500% higher than pre-conflict levels, scaling these solutions quickly is critical. Naval warfare now hinges on balancing economics with cutting-edge technology.